Welcome to Chapter 2, Atoms, Molecules, and Ions, Part 3 Screencast. Well, now in the previous screencast we looked at atoms in some detail, so now let's look at how atoms combine with other atoms to make compounds. When two atoms encounter each other, it turns out that it's the electrons that interact with each other, and that's where the chemical action is. It also turns out that atoms bond together in two basic ways. One is that atoms can share electrons and form what are called covalent bonds. When this happens, when a group of atoms bond and make covalent bonds, it's called a molecule, and this would be an example of a molecule, atoms bonded together, sharing electrons. And when this happens, it's worth noting that bonds typically give a lower energy, more stable substance. So, for example, two oxygen atoms have a certain energy, but if they can bond together and share electrons, they're going to have a lower energy as an oxygen O2 molecule, and they'll be more stable. So this is kind of a favorable thing energetically, and this is one of the driving factors in terms of why bonds form, why molecules form, why compounds form, and why reactions occur for that matter. Now, molecular compounds are usually combinations of one nonmetal with another nonmetal, or possibly quite a few nonmetals combined together. So, for example, carbon with oxygen and or with hydrogen and or with sulfur and or with nitrogen, nonmetals combined together, not having any metals involved. Here are some examples. H2S, hydrogen sulfide, hydrogen and sulfur, both nonmetals. C3H8, also known as propane, carbon and hydrogen are nonmetals. PCl5, phosphorus pentachloride, phosphorus and chlorine are nonmetals. And a few more. Ammonia, NH3, and sucrose, C12H22O11. All of these are combinations of non-metal elements. Now, it's also worth noting that every molecular compound has a definite formula, like C12H22O11 or H2O, and it also has a definite arrangement of its atoms. So this is actually a molecule of a different sugar than sucrose. It's C6H12O6, or glucose, and these atoms of carbon, the black atoms, oxygen, the red atoms, and these sort of off-white ones are hydrogen. To make a molecule of glucose, they need to not only have 6 carbons, 12 hydrogens, and 6 oxygens, but it also has to have exactly this arrangement. So there it is in another form. And with molecular compounds, later in the semester we're going to look at these in much greater detail, but for now we'd at least like to be able to go between formulas and names, and we're going to specifically look at binary or two-element molecular compounds. And the rules for this are reasonably simple. We use prefixes to indicate the number of atoms of each element in a molecule, and we leave the first element's name the way it is, and then the second element's ending we change to IDE. And this is probably easiest to learn or see by example. So here are some formulas and names. We'll do from the formula, figure out the name. So this one has 1 carbon and 2 sulfurs, so we'll call it carbon. The sulfur will change to sulfide, and since we have 2 of them, we'll put a di out in front. So the full name will be carbon disulfide. Now let's go from the name to the formula. Dinitrogen tetroxide, di means 2 nitrogens, and tetra means 4, and then oxygens. So this is going to be N2O4. SF6, sulfur and fluorine. Fluorine becomes fluoride. 6 is hexa, so this is sulfur hexafluoride. And one more going from name to formula, triselenium pentachloride, 3 for tri and then selenium, and penta is 5, and then chloride comes from chlorine, so Se3Cl5. Now there's a second way that atoms can combine to make compounds, and in this second way, one atom can gain electrons and form what's called form a negative ion. It has more electrons, more negative charge than it started with, so it's overall now negative. And then the other atom loses electrons, it loses negative charge, it therefore becomes overall positively charged, and it forms what's called a positive ion. An example would be if we start with a chlorine atom, 17 protons and 17 electrons. It can gain an electron and end up with 18 electrons. Now it has one more negative charge than positive charge. Overall it's negatively charged, and we would call this a chloride ion. On the other side of things, we can have a sodium atom that starts with 11 protons and 11 electrons, and it turns out that it likes to lose an electron, and when it loses an electron, it's now down to 10 electrons. It has one less negative charge, or if you prefer, now it has one more positive charge, and so that will be a sodium ion with an overall +1 charge. And then, of course, a chloride ion negatively charged and a sodium ion positively charged can attract each other to make a compound. So that's what's happening here. The ions that are formed have different charges, they attract each other, and the attraction is called an ionic bond. And this also results in lower energy, like with covalent bonds. So here's the happy NaCl compound, positive ion, negative ion attracting each other. If we go back to the magnesium burning example that we saw in a previous screencast, it turns out that magnesium actually loses 2 electrons. And when it does that, it goes from 12 electrons to 10. It now has a positive charge of +2, and so we would write that Mg with a superscript +2 representing that the magnesium ion has that +2 charge. The oxygen atom, however, is going to gain electrons, and it actually gains 2 electrons, and when it does that, it forms a negative ion. It goes from 8 electrons to 10 electrons. An excess of 2 negative charges gives us an oxide ion that has an overall -2 charge written as a superscript. And then, of course, the compound that forms is written MgO. The +2 attracts the -2, and it looks something like this. And of course, there will be lots of Mg pluses and lots of O2 minuses, and they'll alternate in all directions throughout the actual macroscopic compound. And how did we know that there were the gains and losses of 1 or 2 electrons in the sodium chlorine and magnesium oxygen compounds respectively? And it turns out the periodic table is a big help for that. And the big overriding guiding principle is that these guys, the noble gases, have very stable electron arrangements. They're noble gases or inert gases because they don't react very much, and they don't react very much because their electron arrangement is pretty good the way it is. So this is a good general rule, and we'll get into it in much more detail in further chapters. But the noble gases are very unreactive because they have stable, very stable electron arrangements. There are some elements that will form ions by either gaining or losing electrons, and they'll do that until they end up with a stable noble gas electron configuration. And let's take a look at some of the rules for this. Well, for a few examples first, sodium readily easily loses an electron and forms the Na+ ion. Mg loses 2 electrons and forms the Mg+2 ion. We've seen these already. On the other side of the periodic table, Fluorine readily gains 1 electron and forms the F- ion, kind of like chlorine did. And sulfur readily gains 2 electrons and makes the -2 charged sulfide ion. Aluminum usually loses 3 electrons and forms the +3 ion. It's pretty likely to do that, almost guaranteed. While nitrogen fairly readily gains 3 electrons and forms the N-3 ion. Okay, let's look at these guys on the periodic table and notice some things. In fact, all of the elements in the alkali metals column, including hydrogen, are 1 electron more than the previous noble gas. And they therefore are fairly happy to lose 1 electron and therefore end up with a positive charge. The alkaline earth metals are 2 electrons more than the previous noble gas, and they're very likely to lose 2 electrons and thus form a +2 charged ion. On the other side of the periodic table, the halogens are 1 electron short of a noble gas, and so they are pretty likely to gain an electron and make a -1 ion. The next column, the chalcogens, starting with oxygen, need 2 more electrons to make a noble gas arrangement and therefore make -2 ions, etc. And if we keep going, the nitrogen column, or the pnictogens, tends to make -3 ions, although it's a little less certain than the -2 and -1 ions. And the boron column tends to make +3 ions. In between, the carbon column, well, if it was making ions, you'd say, well, gee, it could maybe make a +4 ion or a -4 ion. And it turns out that that's just a little bit too many electrons to gain and lose, and the elements in here typically don't form ions. They actually make covalent bonds, and we'll do a little more with that in future. Okay, and then note, of course, that the noble gases don't need to form ions. They're pretty happy with things already. And the ones in the middle, we're going to skip for a little bit. It's pretty tough to predict charges of the transition metal elements when they make ions, other than they're metals, and so they typically make positive charged ion of some sort. And we'll do a little more with that in a future screencast. Okay, here is a table from your textbook that shows some of those charges, and you'll notice that we have a little bit of uncertainty in some of these and more than one possibility, and we'll get into that in a little bit as well. Okay, one other generalization is that metals typically make positive ions and nonmetals typically make negative ions. The metals are the ones in yellow here. The nonmetals are the ones in blue.